Hi everyone, welcome back to ChemHelp ASAP. In this video, we are going to be talking about the difference between core electrons and valence electrons. And once we understand our valence electrons, then we can use those to predict our charges. Let's get started. Before we begin, I do recommend getting out your copy of the periodic table, not only so you can see things a little better, but also so that you can mark it up and make notes on it. Now let's talk about electrons. Let's start by taking a look at sodium. So here is my orbital energy diagram for sodium. I have put my electrons in. Sodium's atomic number is 11. Let's just make sure that we have 11 electrons. So we have 2, 4, 6, 8, 10, and then one lone one right there. Core electrons are going to be closer to the nucleus, and core electrons are also in completely filled energy levels. Valence electrons are going to be farther away from the nucleus, and they are going to occupy partially filled energy levels. So if we look at the first energy level, that is only comprised of the 1s orbital. That orbital is filled. It has 2 electrons. Therefore, those 2 electrons are core electrons. Our second energy level comprises not only the 2s orbitals, but also the 2p orbitals. Are those orbitals filled? Yes, they are completely filled. So our first energy level is filled. Our second energy level is filled. Those are all core electrons. Let's look at our third energy level. Our third energy level consists of the 3s orbital and the 3p orbital. Are those orbitals completely filled? No, they are not. Okay, so here are our valence electrons. How many valence electrons in sodium? Simply the one right here. So sodium has 1 valence electron and 10 core electrons. Now, while you can always draw the orbital energy diagram, that takes a lot of time and it takes a lot of space on your paper. So let's do the same thing, but let's take a look at the electron configuration for sodium. So here is the electron configuration for sodium. When looking at electron configurations, I think it's easiest to go after the valence first. In an electron configuration, the energy levels are given by these inline numbers right here. When we're looking for valence, we're looking for the largest of those numbers. And in sodium's case, that is going to be the 3 right here. So then my next question is, how many electrons are associated with that 3 I circled? And there is only 1. That means that all these electrons here are core electrons. And just like with the orbital energy diagram, we have 2, 4, 10 core electrons, and of course just this one lone valence electron. Let's do the same thing with another element. Let's go to oxygen. So here is the orbital energy diagram for oxygen, and I have already filled in all of the electrons. So starting with the 1s orbital down here. That is our first energy level. Is it completely filled? Yes, it's completely filled. It only has the 1s orbital. There are 2 electrons in it. Okay, so the next energy level is the second energy level. So looking at the second energy level, that is going to be our 2s and our 2p orbitals. Are they completely filled? Well, the 2s is completely filled, but the 2p is not completely filled. So our second energy level is going to be where our valence electrons are. So for oxygen, these 2 electrons in the 1s orbital are our core electrons. All of the others are valence. So we have 2, 4, 6 valence electrons for oxygen. Just like we did for sodium, let's take a look at the electron configuration. Here's my electron configuration for oxygen. I am comparing these inline numbers here. I'm looking for the largest, and the largest is 2, and I have 2 of them, the 2s and the 2p. So these electrons here are my valence, and I have 2 plus 4, I have 6 valence electrons. The 1s here, of course, there are just 2 electrons there. Those are my 2 core electrons. Again, it matches up with the orbital energy diagram. My 2 core here are my 2 core electrons here. My 6 valence are my 6 valence here. Now, the cool thing about the periodic table is there are patterns. Let's take a look at some valence electron patterns. We are going to focus in on the alkali metals. These are in the first column right here. I am going to skip hydrogen. We're going to jump in actually with lithium. So here is the electron configuration for lithium. Just like before, I want my largest n-line number, which is going to be my 2s here. How many valence electrons? Well, just the one. Now let's go on to sodium. So that was lithium. We're just going to go to sodium right below it. Here is the electron configuration for sodium. Again, I'm looking for my largest n-line number, which means I am going to go for the 3s here. How many valence electrons? 1. Now moving on to potassium right here. Here is my electron configuration for potassium. Looking for my largest n-line number, that is going to be my 4s. How many valence electrons there? 1. Are you seeing the pattern yet? But let's go ahead and get rubidium, cesium, and francium up. So after potassium, now we have rubidium. Now once we hit rubidium, we start having d electrons. So you can see in rubidium, here are the 3d electrons. But we are still looking for our largest n-line number. So are those D's going to be the largest n-line number? Well, no, they are 3 D's. We have a 5s1 here. That's definitely our largest number. Again, how many valence electrons in that 5th energy level? 1. I know you guys are definitely seeing the pattern here. But let's see what happens when we get larger atoms, especially when we get to the F's. So let's do cesium. Here is the electron configuration for cesium. We have D's again. We have lots of D's. We have 3 D's and now we have 4 D's. But is that our largest number? Nope. Our 6s1 is still the largest number with our 1 valence electron as expected. But what if we add F's? So let's take a look at francium, our last one in the alkali metals. Here is its really, really, really long electron configuration. And you can see here we've added the F's in. But those are 4 F's. Is that our largest number? No, it's not our largest number. Our largest number is 7s1 with our expected 1 valence electron. So I want to illustrate that even when you add the D's and the F's, because when you do the electron configuration, they count back either 1 or 2, depending on which one you're doing, they are never going to be the valence electrons. So what pattern did we find in doing all of this? Well, all of the alkali metals have 1 valence electron. That is handy to know, isn't it? Before we leave the alkali metals, the question you may be asking is, well, do I have to write out the whole electron configuration? What if I use the noble gas shortcut? And I would tell you that is a great idea because the pattern becomes even more evident in the noble gas shortcut. So here are the electron configurations of all of my alkali metals with the noble gas shortcut. And you can see first how much shorter and how much simpler they are. But also notice it makes it very easy to find this 1 valence electron. Our noble gas shortcut goes a long way to pulling out the core electrons. But it doesn't always. So let's work with finding another pattern in the periodic table. Let's work with the halogens. The halogens are over here. They're in either the 7th or the 17th column, depending on what your periodic table shows. And this one, it actually shows both. Let's start with fluorine. Okay, so here is the electron configuration for fluorine. Remember, valence, we're looking for our largest number. So in the case of fluorine, that is going to be 2. It's both the 2s and the 2p. So we have 2 plus 5 or 7 valence electrons. Let's take a look next at chlorine. Here is the electron configuration for chlorine. Again, we're looking for the largest number. That is going to be the 3's in this case. And you can see I have 2 plus 5. Again, I have 7 valence electrons. Okay, but what happens when we go to bromine? Because now we're going to start adding some d electrons. Here is the electron configuration for bromine. We're looking for our largest number, and that is going to be not 3, but 4. And again, I have my 4s and my 4p. I have 2 plus 5. I still have 7 valence electrons. So even though we write this 3D in between, because it is a 3 and not a 4, those are not valence electrons. I'm sure by now you're starting to see the pattern, but let's see how this continues working out with iodine and astatine. All right, so iodine next. Here's the electron configuration for iodine, and let's find our largest number. It's not going to be 4 this time, it's going to be 5, but again, I have 5 S's and 5 P's. 2 plus 5 gives me my expected 7 valence electrons. Again, the 4Ds are in between, but they are 4s, not 5, so they are not valence. Okay, our last halogen, astatine. Here is its very long electron configuration. Okay, so this time we're dealing with not only Ds, but we're also dealing with Fs, but we're still looking for our largest number. So if I'm looking for my largest number, that is going to be, well, certainly the 6. And here are my 6 S's. So again, I have my 2 plus my 5 or my 7 valence electrons. So even though now we have Fs in between our S's and P's, it still is not going to be the largest number. These are 4 F's, and we're looking at the 6s and the 6 P's. So they are not valence electrons. Okay, so just like we did with the alkali metals, let's take a look at the electron configurations with the noble gas shortcut, because in this case, it will not pull out all of the core electrons. All right, so here are all our halogens, again, with the noble gas shortcut, and wow, it really makes the electron configuration so much shorter, doesn't it? So you can see for fluorine and for chlorine, the noble gas shortcut does make it very easy to see our 7 valence electrons. But once we get down to bromine, we have to be careful and make sure that we're just pulling the electrons from the 4s and the 4p. So the electron configuration, again, still shows these D electrons, but they are not valence. You can see the same thing is true with astatine. Down here, we want the 6s and the 6p, and these 5Ds and 4Fs are there in the electron configuration, but they are not valence. So noble gas shortcut is very helpful, but keep your wits about you. You're still looking for those largest inline numbers. So we have a new pattern. These guys all have 7 valence electrons. Now you're probably wondering, do any of these other groups also have patterns? Why, yes they do. Let's go find them. Instead of doing all the electron configurations for all the elements, we are just going to summarize our patterns. So we already found that the alkali metals have 1 valence electrons and the halogens have 7. What about group 2? What about the alkaline earth metals? Well, let's just take a look at beryllium here. If you're doing the noble gas shortcut for beryllium, of course you're going to use helium, and then what comes after that? Your 2s orbital. And how many electrons? There would be 1, 2 electrons. So beryllium has 2 valence electrons. Can you guess how many valence electrons magnesium has? That's right, 2. Calcium, 2. Strontium, 2. Barium, 2. Radium, 2. So our alkaline earth metals have 2 valence electrons. Switching over to the right-hand side of the periodic table, of course, we found that the halogens all have 7. But what about group 6 or group 16, starting with oxygen? So if we're doing the noble gas shortcut for oxygen, of course, we're going to use helium. Then we're going to the 2 S's and the 2 P's. How many electrons total are going to be there? They're going to be 2 in the 2 S's, and then 1, 2, 3, 4 more here in the 2 P's. That is 6 valence electrons. So oxygen has 6 valence electrons. Just like before, it moves down the group: sulfur, selenium, tellurium, polonium. My guess is by now you're starting to see a larger pattern because you're noticing how these valence electrons are matching up with these group numbers here. 7 and 7, 6 and 6. So you probably don't even need to do the electron configuration for nitrogen. You could probably guess that it has 5 valence electrons, and you would be correct. Because again, if we started at helium, there'd be 1, 2, 3, 4, 5 valence electrons to get to nitrogen. So let's go ahead and just fill the rest of these in because you know how this is going to go. Carbon's group has 4 and boron's group has 3. This does beg the question, What's going on with these guys down here, and of course with the F's as well? Well, remember, your F's are going to count back 2, so they are never going to be valence electrons. These metals in here, these are your transition metals. Things start to happen with the electrons, and they actually start to move around a little bit. So for example, iron sometimes has 2 valence electrons and sometimes has 3 valence electrons. You can always use the electron configuration to predict the expected number of valence electrons, but whenever you're working within the transition metals here, things do sometimes get a little bit squirrely and our rules and predictions start to break down. Once we can predict how many valence electrons we have, then we've got a really powerful tool to predict the charge on that element when it becomes an ion. This is super important in ionic compounds. So to lay a little foundation, let's look at the noble gases. We didn't specify this when we went through our pattern of valence electrons, but the noble gases all have 8 valence electrons, with the exception of helium here, because helium and hydrogen always feel like they have to be different and special. However, helium does have a full shell. It has 2 electrons in that 2s orbital. It cannot take any more. So it couldn't take 8 electrons even if it wanted to. The rule of thumb is all of the elements are looking for the stability of these noble gases. They are looking to have a full outer shell or 8 valence electrons. So if I take a look at fluorine here with its 7 valence electrons, it only needs 1 more valence electron to make that jump to 8. This is one reason why fluorine is so reactive. So when it gains that electron to then have 8 electrons, it now has 1 more electron than protons. That means the charge on that fluorine anion is going to be -1. And yes, I did mean to write it with the sign on the right-hand side. That is generally how we write charges on ions. Let's pop over to the left-hand side of the periodic table. Let's take a look at lithium. Again, I just want to skip hydrogen because hydrogen and helium can be a little bit different. So lithium has its 1 valence electron. Now it could try and gain 7, so it could go all the way across and have 8 valence electrons. But it's actually much easier for it to take that 1 valence electron and ditch it, because if it loses 1 electron, then it looks exactly like helium with 2 valence electrons. So on the left-hand side of the periodic table, these elements tend to lose electrons and become cations. So fluorine, when it gained 1 electron, it ended up with a charge of -1. Lithium, when it loses 1 electron, is going to end up with a charge of +1. Again, I do write the sign to the right of the number. Let's start to move inward just a little bit. So we looked at lithium. Let's look at beryllium. We know it has 2 valence electrons. So it can either try to gain 6 electrons, or it can just dump those 2 electrons. Well, it's a lot easier to get rid of 2 electrons than try and find 6 to gain. So beryllium is going to lose not 1 electron, but 2 electrons. And then it would also have the electron configuration of helium. You can see where this is going. When beryllium loses 2 electrons, it is going to end up with a +2 charge. Back to the right-hand side of the periodic table, let's look at oxygen. Now, fluorine just needed to gain 1 electron to look like neon. How many electrons is oxygen going to need to gain to look like neon? Well, oxygen is going to need to gain 2 electrons to look like neon. Now, you could argue that it could dump 6 electrons and become a cation, but again, it's easier to gain 2 than try and dump 6. So oxygen is going to gain 2 electrons. What is that going to do to its charge? It's going to give it a charge of -2. Again, I know you're already seeing this pattern. Nitrogen has 5 valence electrons. It needs to gain 3. So it is going to have a charge of -3. Boron has 3 valence electrons. It is going to lose those 3 valence electrons. It's going to end up with a charge of +3. Now, once we hit group 4 here with carbon, you're probably thinking, well, it could gain 4 or lose 4, but it actually is going to do neither. So these group 4 elements here, generally do not become ions, but they form what we call covalent compounds. So they are going to share electrons instead of gaining and losing electrons. We will go more in depth with this concept when we get into our naming. So these are the patterns of valence electrons and ions in the periodic table. I know some students, when they start chemistry, they try to memorize all the ions. So they'll try to memorize that sodium becomes a +1 cation and magnesium becomes a +2, whereas chlorine becomes a -1. As a student, I always hated to memorize. So if I could find patterns, I was always much happier finding patterns and using those. So I hope that these patterns also help you. I hope you now have a better understanding of the difference between core electrons and valence electrons, and that you can appreciate how important it is to know those valence electrons. Thanks so much for watching.